All right, so welcome, AP Chemistry, Tuesday, September the 29th. Okay, so we just went over all the lab stuff. You have your quiz on Friday. Okay, and for those of you at home, I did make a unilateral decision about 10 minutes ago that I will include about 5 minutes, 1 to 2 ionic equations, equations to write total and net ionic equations for on the quiz. So it'll be a lab quiz and a total and net ionic reactions quiz. But again, only 1, 2 at the most for the ionic equations. 15-point quiz. All right, now, I should have had this already pulled up, but at the end of the class, I know that you all watched this video intently, okay? But at the end of the class, we were looking at this on the dissolution process thing that you had to read last Wednesday. We looked at this slide off of the article that you read. Okay? Now, what does this tell us? It continues to be quiet. There were crickets around, we could definitely hear them chirp. Come on, so what does this tell me? To make a solution, what 3 things have to happen? The solute has to break apart from each other. The solvent has to break apart to allow room for the solute. And then what has to happen? They have to combine together in order to be able to dissolve. Okay? So what we want to look at today are look at these processes in depth. Okay? And look at the energy changes that are occurring and what type of attractive forces do we have to break in order to get the solute to break apart. Now that's going to depend upon what type of solute it is, whether or not it's an ionic solid or whether it's a covalent solid. Now how can you know again something's ionic or not, right off the bat? If it has a metal, if the first thing in the compound's a metal, we know it's ionic. If the first thing in the compound's a non-metal, it's covalent. Okay? So, we have to look at those attractive forces, what's going on, and then what's holding the solvent together, and then what is the attraction between the solute and the solvent, and that really is going to be the most important thing. Now again, when you watched that video yesterday, I showed a video in the video. Okay? What was the video of? How things separate. Specifically what thing? It was salt putting into water. And it showed the water molecules coming in and hydrating, surrounding this, where, I put them all away for some, I gotta pull them back out again. I'll do that later. Pulls this off, surrounds it, hydrates it, okay? So, when we look then, let's get organized on this. There are 3 steps to the solution process. The first one is the solute particles have to break apart. Okay? Now, we have 2 different types again, ionic solutes, which we call salts. The ionic bond holding the charged ions in the crystal must be broken. The energy to do this, and this is an important term, so when you write this down, highlight it or underline it, do it in all caps, lattice energy. Okay? So the energy that it takes to break the Na plus from the Cl minus is called the lattice energy. Now some books define it as the energy released when the ions come together. But it's going to be the same number. It's just whether it's positive or negative, whether it's released or absorbed. you have to understand, breaking up is always hard to do. Okay? If you have to break up with a boyfriend or girlfriend, you stress over it, try to figure out the exact right wording. You know, nowadays you guys can text and just say, hey, I think we should just be friends. You know, texting. But in my day, we had to actually call on the telephone and talk, or do it in person. And it's very challenging. It's stressful. You have to put a lot of energy into it. It's nothing fun. So breaking bonds always requires energy. Would that be endo or exothermic? This process requires energy, meaning this process is endothermic. You put energy into it. You have to break them apart. Now, where is that energy going? When you put the energy in to break these apart, you're putting energy in, so it's absorbing it as potential energy. It now has the potential to come back. So let's just say that it takes 10 kilojoules to break a mole of these apart. Let's just say 10 joules to break this bond. Now this has absorbed 10 joules of potential energy. When it comes back and bonds, it releases 10 joules of energy. And the potential energy goes down. So the lattice energy is how much energy you have to put in to break the bonds. Breaking the bonds, this solute to solute is always endothermic. And we're going to call that one delta H1. Okay? Delta H is your change in your heat. Fancy word for it is your change in enthalpy. Okay? But enthalpy is just a Latin, what we're going to talk about, meaning heat. And so we use delta H. Okay? Now, if it's a covalent substance, we have to break the intermolecular forces, the IMFs, because it's molecule held to molecule held to molecule. And we have 3 IMFs. Now I have the first one up there, London dispersion forces. Does anybody remember the other 2? Dipole. Hydrogen bonds. Okay? So we have London, and these all come in the next one, but London, dipole, and hydrogen bonds. Now they kind of increase in strength, but here's my analogy on this one. These IMFs holding molecules together are very weak compared to the bonds holding ionic compounds together. Okay? So we're going to talk about the strength of these London forces, dipole, hydrogen bonds, but all 3 are weak. I always say they're like kindergartners versus an adult, you know, how strong they are. Okay? So we're going to talk about on these, which kid is the strongest one on the kindergarten playground. So they're all still going to be weak, but there's varying levels of weak. Okay? So the first one, London dispersion forces, and you can abbreviate that even on the AP test, LDF, because we don't like to write it out all the time. So your LDFs, London dispersion forces. Sometimes they're called induced dipole. Let me write that down. Okay? I'm just going to go one. Also called induced dipole or instantaneous dipole. What does the word induced mean? When have you heard the word induced?
All the time.
Anybody have a aunt, sister, or somebody get pregnant? Induce labor. Okay? What does that mean to induce labor? Force it to happen. It's not happening naturally. So they give a chemical to induce, to make it happen. It's not it is not happening all on its own, okay? So, and an induced dipole is one that doesn't form on its own, it's forced to happen. It's also called an instantaneous dipole because it only lasts for an instant. It's a natural attraction between all molecules. So, whenever a question asks for what are the IMFs between these molecules, or what IMFs are present, London force is always an answer. All molecules have LDFs. Okay? It's the only attractive force between nonpolar molecules. Okay? Only IMF between nonpolar molecules. So, they're the most significant in nonpolar molecules. But we're going to have a dipole-induced dipole. Now, the way that this works is if I take a methane. Methane is a symmetrical molecule. The carbons and hydrogens really are nonpolar. It's an even sharing of electrons all the way around, which means that the electron cloud is symmetrical, evenly distributed. Okay? So there's no dipole, there's no two poles, it's not a polar molecule, it's a nonpolar molecule. But when water comes in, with its negative and positive ends, when this starts approaching here, well, what do we know about negative electron cloud and negative electron cloud? They're going to repel. And so this electron cloud is going to get distorted. Now it's no longer symmetrical. So now we have a positive end here and a negative end here. Does anybody remember, I talked about this on the video, but what is that? This is a Greek letter delta. What does it mean? Capital, the triangle means change. This is like your integral symbol is what it's supposed to look like from calculus. Okay? It means partial positive and partial negative. If it was an ion, a complete transfer, we'd write positive and negative. But this means partial charge. It indicates polar versus ionic. It indicates that the electrons are just unevenly shared, they're not completely transferred. You just get a positive and negative end in our molecule, you're not having true ions. Okay, we good with that? All right, so now this is positive and this is negative. So now if another water came along, like this, where this is positive and this is negative, there is going to be some kind of an attraction between the water and the methane. Now water is called a dipole. This is now an induced dipole. So this attraction right there has a very creative name. It's called dipole-induced dipole attraction. The attraction between any polar molecule and a nonpolar solute is going to be called a dipole-induced dipole. Okay? This is going to be extremely weak, because as soon as this bounces off of it, this is going to go back to being symmetrical, which is again why we call it instantaneous. It only lasts for a second. So the electron cloud is constantly shifting and moving and being distorted, but the positive and negative ends are never constant. It's constantly changing, and so the attraction here is very weak. As a result, water molecules, does anybody know, just, we're going to get to this, but anybody know in water molecules what the major force holding the molecules together is?
Hydrogen bonds.
Hydrogen bonds, okay? Which are the strongest of the three IMFs. So, and I'm going to cover this in more depth, but I'm just kind of foreshadowing a little bit here. This dipole-induced dipole is very weak. As a result, it's not strong enough to break the hydrogen bonds that are holding the water molecules together. So the water molecules, that solvent to solvent, having to separate, Water saying, I'm not gonna separate, I'd much rather be, you know, with another water molecule than with nonpolar methane. So as a result, nonpolar molecules do not dissolve in polar water. Now, in chemistry 1, we just say like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. Now we have to explain that for AP. We have to explain it in terms of these attractive forces. We have to say that methane is not soluble in water because the dipole-induced dipole attractions between the two are too weak to overcome the much stronger hydrogen bonds holding the water molecules together. Consequently, water molecules do not separate and the two do not dissolve. Okay? So we have to talk about those types of attractive forces. So a London force is just a natural attraction due to the distortion of the electron clouds as they interact with one another. So even nonpolar molecules, two nonpolars, if I have a CH4 and a CH4, okay, when they begin to interact, they're going to do the same thing. They're going to distort. Okay, this becomes positive, this becomes negative, this is positive, it's going to move apart, this is negative. So they'll bounce off of one another, but another CH4 comes along and it has the exact opposite. The positive end of it comes to here, and there's going to be that weak attraction. Now it's very weak. Methane, the molecules will not stick together until the temperature is around negative 200. I don't know what the exact temperature is, but it's close to negative 200 degrees Celsius. What does that mean about the motion of the molecules at negative 200? Very slow. Okay, very little energy can be in the molecules because it just takes a little bit to break them apart because the attraction is so weak. Now, as we go to bigger molecules, C2H6, C3H8, C8H18, octane, if you go and fill up your gasoline, they talk about the octane rating, C8H18. The bigger the molecule, the bigger that electron cloud is, which means it's more smushable. The fancy word for AP, it's more polarizable. It distorts more, and so the negative and the positive become more distinct. So London forces increase with the size of the electron cloud. More electrons equal stronger London forces. Okay? So just now, this is a semantic thing. Okay? We're going to look at the molar mass, the molecular weight. The greater the molecular weight, the stronger the London forces. But you can't say it's a bigger molecule or a bigger molecular weight. The answer you have to give for AP is it's got a bigger electron cloud. The electron cloud is more polarizable, okay, because it's larger. As a result, the London forces are stronger. Okay? So the London forces always varies with the size of the electron cloud. But the practical way, bigger molecules, the heavier it is, the bigger the electron cloud is going to be. So we don't count electrons, we just say, okay, something has a molar mass of 100, it's going to have more electrons than something has a molar mass of 50. But your answer can't say that. Your answer has to say the bigger molecule has a larger electron cloud, which is more polarizable than the smaller molecule, therefore its London forces are stronger. Okay, you good with that? Nobody's writing any of that down, but you just got to be able to say that. Okay? So bigger molecules. Seems like there was one more thing I wanted to say about this. I think it was the size of the electron cloud. All right, so that's London forces. Natural attraction. Does everybody understand how it works? You'll never have to draw this on an AP test as far as the size of the electron cloud. I'm just using this to kind of illustrate why the bigger the electron cloud and how this London force forms. Rather than just saying it's a natural attraction, we want to know why and how does that work, right? We don't want to just memorize something. We want to understand the why behind the what. Okay? So that's the first one. Whew, good stuff here. By the way, all of this is in chapter 13. Because I know you probably want to read the book as well. missing a page. All right, so our second type of attractive force are dipole-dipole. This one is super easy to kind of see. If we take HCl, okay, first off, what does it mean to be dipole? Two poles. What causes it to have two poles? Okay, where the electrons are, why aren't the electrons evenly distributed in a polar molecule? They have different numbers of valence electrons, that's true, but that's not the factor. There you go, very good. And the electronegativity. What the heck is electronegativity? Electronegativity. Remember the word? You had to look it up on the chart. Okay? It's the attraction, but not just for any electrons, for a shared pair. So the electronegativity is how much is chlorine pulling on this pair of electrons that's shared versus how much is hydrogen pulling on that pair of electrons. Okay? And so electronegativity is an atom's attraction for a shared pair of electrons. Okay, E minus is always an electron. We're going to use En for electronegativity because we don't want to write that word out all the time either. Okay? I forgot that I had it written right here. Okay? Polar molecules generally contain fluorine, oxygen, nitrogen, or chlorine. So you don't really need to write this part down if you haven't done it yet because it's right there. Okay? I call it phone call, F-O-N-C-L. Phone call, just the phonetic is kind of like a license plate, you know, trying to figure out what it stands for. But F-O-N-C-L, those are the big four most electronegative elements. Those are the ones that do not share well with others. They hog the electrons. They're going to be the negative end of a polar molecule. So, if a molecule contains fluorine, oxygen, nitrogen, or chlorine, there is a high probability it's a polar molecule. If it doesn't contain one of those, there's a high probability it's a nonpolar molecule. When we get into bonding and molecular shapes, we'll talk about how to really determine whether a molecule's polar or not. But for right now, we're just going to look for these four elements. Any one of these four, not all four of them, any one of the four present. Okay? If any one of these four is present, we're probably going to be a polar molecule, which means it's going to have a dipole-dipole attraction. So, the electronegativity. Chlorine's electronegativity, and this is on your periodic table. You do not need to memorize this, but the trend. We did learn the trend last year, or in Chemistry 1. Okay? Does anybody know which one is the highest electronegative element? Fluorine, top right. We exclude the noble gases because they don't bond with anything. They really have very low electronegativity. So fluorine, which one's going to be the least? Francium, bottom left. So that's your trend. As you move left, it gets stronger, greater electronegativities. As you move down, because the electrons being attracted can be farther away, it's weaker. Okay? So just remember, fluorine is the greatest. Francium is the smallest, that's your trend. As you go up to the right, it gets greater. These four are your biggest four. Okay? Most electronegative. So chlorine, you look, but if you look on the periodic table that I gave to you on the back, it'll tell me that the electronegativity is 3.16. It's a scale from 0 to 4. Okay? Hydrogen's is 2.20. So there's a difference of 0.96. Okay? That's your difference in electronegativity. We use 0.3. If the difference is less than 0.3, it's nonpolar. Between 0.3 and 1.7, it's polar. Now, where does the 1.7 come from? On the periodic table that I gave you, at the top, okay, you get it big enough to where y'all in the back can see it. Okay, so this is the difference in electronegativity on the top between the two atoms that are bonding. Then this is the percent ionic character. How uneven is the sharing? The greater the percent ionic character, the more uneven the sharing is, the more unevenly distributed the electrons are. What happens at 1.7? What's the percent ionic? 51, right? What does that mean? Well, it's more ionic than it is covalent, right? Because we're over 50%. So we use 1.7 as the cutoff. If the difference in electronegativity is greater than 1.7, it's going to be an ionic bond. Now, it's really not a complete transfer. It's not really until it goes into water does the transfer of electrons become complete. But we call it an ionic bond. Now, again, on the periodic table, these are your lowest, these are your highest. So you're going to have the greatest difference between in electronegativity, so we're going to have an ionic bond. Two nonmetals bonding together are going to have similar electronegativities, therefore the difference is going to be much smaller, so we're going to have polar, nonpolar bonds. Okay? But if we have fluorine, oxygen, nitrogen, and chlorine, they're significantly greater than just about everything else, then we have polar covalent bonds. Y'all with me on that? That's very important, just to have that basic understanding. The periodic table tells us. But that's why metals and a nonmetal is ionic. Two nonmetals are going to be covalent. But now we're going to differentiate nonpolar covalent and polar covalent. Nonpolar is not going to have phone call, polar will. Okay? Whew. Lots of heavy duty good stuff in here today. My word. I'm starting to sweat. I'm getting so excited. I can see the excitement all over y'all's face. Even though you have the mask on, I can see it in your eyes just glowing. God, Mr. Hobbs, this stuff's exciting. I always wanted to know how this worked. All right, so dipole. Oh well. A natural attraction. Generally speaking, dipole attractions are stronger than London forces. However, lately, the past 3 to 5 years, they started asking questions where they give a big nonpolar molecule and a small polar molecule. So the big nonpolar has stronger London forces. Sometimes it's going to be greater than the polar dipole of the smaller molecule. The way we tell that is the higher boiling point always means greater attractive force. Okay, so write that in the margin out here. Higher boiling point means stronger IMFs overall. So we have to look at what's present. So if they give you data with boiling points, whatever one has the highest, it's got the strongest attractive forces. So we just kind of go through and we'll look at some practice AP questions that actually do that. Okay? All right, so let me just give you an example of a dipole-dipole. We'll use HCl again. That's how I started with this. Okay, this is negative, this is positive. We put another HCl with its negative and its positive. This attraction right here is your dipole-dipole attraction. The positive end of one attracted to the negative end of the other. They don't have to be the same molecules. If water was to come in here with its negative and its positive, that's a dipole-dipole attraction. Okay? So any polar molecules, the positive end of one attracted to the negative end of the other. Obviously, the more polar it is, the bigger the difference in electronegativity, the greater the percent ionic character, which means that the positive and negative are going to be stronger. So, polar molecules vary in strength. Just like magnets. You got magnets on your refrigerator at home? Okay? You got the cheap ones that you can maybe hold a picture on, but if you want to hang that calendar or something that's a little bit heavier, the cheap ones just kind of slide down the refrigerator, but then you got to find that Mac Daddy magnet that will hold the heavier thing on there. They're both magnets. They both have a north and a south pole, just one stronger than the other. Okay? Same thing's going to happen with polar molecules. The bigger the difference in electronegativity, the more polar it is, the stronger the dipole-dipole is going to be. All right, uno más. When in doubt, the answer is hydrogen bonds. Why is one stronger than the other? Always look for hydrogen bonds. Okay? So we'll start with this. Okay? It's a special type of dipole-dipole attraction. Okay? Special type. It's where a hydrogen gets trapped between two highly electronegative elements. Now this time it's only foam. Chlorine is too big to where it really doesn't form hydrogen bonds. So it's just fluorine, oxygen, and nitrogen. And the hydrogen has to be directly attached to that. So if I have HF and HF, fluorine is the most electronegative element. Fluorine is the element that shares the least. Okay? You guys are already not listening. I'll let you keep writing. I'll just wait and let you catch up. That's why I like to write the notes on the board, but I'm being lazy today. Because I really want these to be orderly, plus I like my color picture.
Pictures are nice.
And I'm going to, after you write them all down, I'm going to post all these. There's something about writing it, though, that helps you retain it better. Okay. So, fluorine, which one's going to be my positive, which are my negative ends here?
Hydrogen. Hydrogen's positive.
Okay, and hydrogen's positive, fluorine's negative, hydrogen's positive. Now, what makes this unique, why it's a special type of dipole-dipoles, because how many electrons, valence electrons, well, total electrons does hydrogen have? Try again. One. Okay? It's got one valence electron. So if that one electron is being pulled strongly this way, what's left? Nothing? What are the two parts of an atom? Which are where? We have the nucleus and we have the electrons, right? So hydrogen is atomic number 1, so what does that mean? One proton. So if that one electron is getting pulled away, that proton, the nucleus, is naked and exposed. There's no electron negative shielding it anymore, nothing blocking that positive charge. So we have a very distinct positive charge. So we talk about acids being the H+ ion. An H plus ion is nothing more than a free-floating proton. H plus ion is one proton, one electron. You take the electron away, all you have left is a proton. So we have a very strong, distinct positive charge here because the nucleus is totally exposed. On the other hand, fluorine is the most electronegative element, which means the electrons are pulled strongly towards it, so the negative is very strong. So we have an exceptionally strong hydrogen bond between the two. Now, here is a picture of the hydrogen bonds in water. Okay? When water molecules combine, you get a hydrogen trapped between two highly electronegative elements, two oxygens. This is your hydrogen bond. This bond right here is a covalent bond. It's a polar covalent bond. This is your IMF right here. Your intermolecular force, inter meaning between. Okay? So this is your hydrogen bond. It's the strongest of the three. Okay? Still a kindergartner. Water still boils at 100 degrees, which is considered to be a low boiling point. However, if it weren't for hydrogen bonds in water, water would be a gas at room temperature. If it weren't for hydrogen bonds in water, ice would sink in liquid water. Instead it floats. It's one of just a handful of compounds, substances that float in their liquid, that are less, the solid is less dense than the liquid. What would happen to a marine life in northern parts of the world, or extreme southern parts of the world, if ice sank? Water levels would be higher, but then they would freeze solid too. Okay? Because right now the water freezes on top and it kind of insulates the rest of the water from freezing. But if it sank, it would all freeze. So when bonds form in water, the water molecules actually move apart to form what we call an open crystal structure. I gotta build it. You need a break anyway. Breathe. Gotta break out my toys. I'm gonna spill some water. Okay? Alright, so I have my water molecules. Okay? When they're a liquid, they have enough energy, they're all kind of crammed all right next to one another like this. Okay? But when they go to form hydrogen bonds, there's only certain ways the hydrogen has to attach to an oxygen. Oh, let me see if I can continue to break them apart. Okay? One more. Like this. 1, 2, 3. So it forms these 6-membered rings. Okay? These 6-membered rings that look like this. Now notice there's this big opening in the middle. So the molecules have pushed apart, they become less dense because of the formation of the hydrogen bonds between the water molecules. Okay? When they melt, those hydrogen bonds stretch and break and the molecules can move. They still roll around one another, but they can move. Now, we don't get much snow down here, but how many points does a snowflake have? Always. 6. Because it's when the water vapor freezes, it forms this hexagonal open crystal structure, and then the points grow off of each of these parts of the hexagon. All snowflakes have 6 points. Now they say every snowflake is different. Everyone's unique. I don't know if anybody's ever gone and measured, how they know that. I would bet by the bazillion snowfalls that happen, 2 snowflakes are pretty close to the same. That's just me. Okay? So, and again, this is what I was going to show earlier, is when water comes in to this, the water molecule comes in and attaches. This is the Na+, so the oxygen attaches to it and then hydrates it to where floating around in the water, it's really going to look like Okay, so in water, the Na plus is completely surrounded by the H2Os. Okay, so it's hydrated. It pulls it into solution. Then another more water molecules come, but now with the chlorines, the hydrogens are going to stick to the chlorines, pull it into solution, and completely surround it. So it keeps these from coming back together. Whoops, coming back together again, because they're hydrated. Now the water molecules are still attracted to each other, but they insulate. So when sodium chloride, salt dissolves, any ionic compound dissolves, they get hydrated, surrounded by the water molecules. Okay? That's from the past. All right. Does everybody understand hydrogen bonds? Two things that you got to look for. Foam, fluorine, oxygen, nitrogen, and that the hydrogen is attached directly to that. Okay? We have fingernail polish remover, acetone. Okay? Actually, I think acetone has 2 carbons on each side, but it's got the oxygen in the middle. Is the hydrogen attached to the oxygen? It's got oxygen and hydrogen in it, but is the hydrogen attached? So what does that mean about H bonds? No hydrogen bonds. The hydrogen has to be attached to the nitrogen, oxygen, or fluorine. So ammonia is another common substance that looks like this. So we have an attraction, that we have a hydrogen attached to the nitrogen. So when another ammonia or water or anything comes along, you can form hydrogen bonds. Okay? Alcohol. Alcoholic beverages. That's ethanol. That's the alcohol in alcoholic beverages. It's got this OH. So water can come in right here and attract that hydrogen, forming a hydrogen bond. As a result, alcohol is 100% soluble, and with 2 liquids, we use the term miscible. They're 100% miscible in one another. You can put any amount of alcohol in water, any amount of water in alcohol, they're going to mix, because there's such a strong attraction between the solute and the solvent. Okay? Hydrogen bonds. What 3 elements?
Fluorine, nitrogen, oxygen.
Fluorine, nitrogen, oxygen. All right, let's go fluorine, oxygen, nitrogen, foam. Okay? And what else must be true?
The
Hydrogen has to be bonded directly to it, not just in the same molecule, but attached directly to it. Okay? That's huge. Okay, so those are our 3 types of IMFs. Those are the solute to solute bonds. All of that was solute to solute. Those are the solute to solute bonds that have to be broken in order for a covalent substance to dissolve. Okay? London, dipole-dipole, hydrogen bond. Now, solvent must overcome the attractive forces between themselves to make room for the solute particles. This requires energy to stretch and break the bond. This energy is going to be much, much less. We're still going to call it delta H2. Okay? But then the solute to solvent, that's the key. There has to be an attraction between the solute and the solvent in order for any of this to happen at all. Because it's really that attraction. It's the attraction of the water to these ions. That's what pulls the ions apart. The ions aren't just going to break apart on their own. It's water pulling them into solution. AP loves this word too. Dissolution. That's a fancy word for dissolving. Those of you at home can fast forward for a couple of minutes while they're copying these notes down, but you ought to be copying the notes down as well. Because I know you want to take notes as you're watching these videos, just as if you were in class. Because the notes are going to keep building on each other. That'll help you stay more attuned to the video as well, if you're actually taking notes on it. It's the only way I know to give you the same in-class experience since you're only coming 2 days a week. I'm assuming you're to that point at least. That's gonna be good. Okay, so the solute to solvent attraction. If the solvent, if the general term is solvation. If the solvent is water, we call it hydration. That's what we talked about, and that's what the video showed of the water coming in and hydrating the ions, okay? This is the process of solvation, hydration, the solvent molecules attaching to the solute and pulling them into solution. So that the net result and the final concept or takeaway is putting all this together. This attraction between the solvent and the solute has to be great enough to overcome either the lattice energy of an ionic compound or the IMFs holding covalent compounds together. Okay? The solute to solvent attraction has to be great enough. Well, I told you with nonpolar that dipole-induced dipole is too weak to overcome the hydrogen bonds holding water molecules together. But with salt, when the water attaches and you get 3, 4, 5 water molecules attaching these ions, that is strong enough to pull the ion apart, to break that lattice energy and pull it into solution. So the first two processes, solute, solute, and solvent, solvent, really occur because of this third one, hydration. Bonds forming always releases heat. It's hard to break up, but man, when you go out and start dating someone and the sparks begin to fly, that's when things really heat up, right? And so that's a natural, when the bonds form, energy is always released. Breaking bonds always requires energy. Forming bonds always releases energy. So in our solution process, we have 3 delta H's. Our delta H of solution, the overall delta H of solution is equal to delta H1, delta H2, and delta H3. We'll pick up with this tomorrow, but just real quick, if this is positive, this one's always positive, this one's always negative, what's going to determine the sign of the overall heat of solution? These are the individual steps. What's going to determine this sign? Not necessarily just H3. You got 2 positives and 1 negative. What's going to determine the sign? Not that hard, y'all. You're going to have to ponder it. Simple math. 2 positives, you got the positives, you got the negative. What's going to determine the sign? You have a +3 and a -2. What's the sign going to be? Plus. If it's a +3 and a -4, what's the sign going to be? Negative. Right?
So you got 2 pluses and 1 minus.
I know, but how big are each number versus the delta H3? How big is that number? So the sum of the H1, H2, is it bigger or smaller than H3? That determines the sign. Add love. Have a great day.